Have you ever wondered how artificial intelligence, specifically those massive large language models we hear so much about, truly learn to solve complex problems? What if I told you that sometimes even wrong or completely random feedback can actually make them smarter? Sounds pretty counterintuitive, right?
It absolutely does. And today, that's the fascinating paradox we're diving deep into. We're exploring a groundbreaking research paper that really challenges our assumptions about how LLMs refine their abilities, especially in tough tasks like mathematical reasoning. This study meticulously investigates the effectiveness of various, sometimes, bizarre reward signals within a training framework known as reinforcement learning with verified rewards, or RLVR. We're going to unpack why certain models, particularly from the Quinn family, show surprising improvements even from what seem like highly spurious, nonsensical rewards while others don't. This divergence, as we'll see, offers profound insights into their fundamental reasoning abilities and the hidden mechanisms at play.
Okay, so our mission in this deep dive is to give you a crystal clear understanding of the nuances of these training signals and the underlying mechanisms that make them work, or crucially, why they don't work for some models, and the critical implications this research holds for the future of AI. You'll walk away with a shortcut to understanding this cutting-edge research, complete with some truly surprising facts and clear explanations that, hopefully, cut through the complexity.
Right. So, to set the stage, let's quickly establish the general context of RLVR. This technique is incredibly important for refining LLMs, particularly for tasks where answers can be definitively checked, like in mathematics. Traditionally, RLVR relies heavily on what we call supervision signals. Think of it as giving the model clear, precise feedback on whether its answers are correct. This has always been considered the gold standard, based on the logical assumption that models need accurate examples to learn effectively.
Right. Makes sense. Feed it good info, it gets better. But this is where the paper takes a fascinating turn, doesn't it? The researchers decided to push beyond that gold standard feedback and explore a whole spectrum of truly unconventional reward signals. And what they uncovered next was genuinely surprising.
Indeed, the study systematically defined and explored 5 distinct types of rewards, ranging from the ideal to the utterly perplexing. First, we have ground truth rewards. This is the baseline. The model gets a reward only for verifiably correct answers. This is the gold standard, high-quality feedback we expect.
Okay, the standard approach. Got it.
Next, there are majority vote rewards. Here, instead of using the actual correct answer, the model is rewarded based on the most common answer it generated itself during its initial pre-RLVR phase.
Oh, okay, so even if its most common guess was wrong.
Exactly. If the model guessed A more often than B or C, then A becomes the reward signal, even if A was actually wrong. It's a form of self-supervision, based on the model's own prior consensus, basically.
Interesting. Okay, what else?
Then, they introduced format rewards. This completely disregards mathematical correctness. A response simply receives a reward if it contains a non-empty boxed expression.
Like just putting the answer in the right kind of box format?
Precisely. Imagine the model just needs to put something in the designated answer box,
Yeah.
regardless of whether the number inside is right or wrong. It's purely about following the prompt's formatting instructions.
Huh. Okay, that's number 3. What's fourth?
Fourth, random rewards. This is pure noise. Responses are assigned a reward of 1 with a fixed probability, say 50%, and 0 otherwise, completely regardless of correctness.
Wait, just random, like flipping a coin.
Exactly like flipping a coin for every answer and giving a reward based on the flip, not the answer itself.
Yeah.
You'd expect this to teach the model absolutely nothing useful, right?
Yeah, you really would. Okay, and the last one sounds even weirder.
And finally, the most counterintuitive one, incorrect rewards. In this scenario, the model is deliberately rewarded for giving incorrect answers. The study achieved this by first using majority voting to identify consistently incorrect answers, and then rewarding responses that match these specific incorrect labels.
Wow. Okay, so ground truth, majority vote, format, random, and even incorrect. Rewarding mistakes. That's wild. Listening to that last one, incorrect rewards, it sounds like trying to teach someone by telling them to fail. You'd expect total chaos, right? So what did they find when they actually applied these rewards, especially the weak and, frankly, nonsensical ones, to these LLMs?
Well, what's truly fascinating are the divergent results they found. Let's focus on the Qwen 2.5 math models first. Despite how, pathologically designed some of these rewards seem, all of them, yes, even the random and incorrect rewards led to significant improvements in math performance for these Qwen models.
Get out of here. All of them. Even random.
Yep. For example, on the Math 500 benchmark, The Quinn 2.5 Math 7b model showed remarkable gains. Ground truth rewards gave a substantial plus 29.1% accuracy gain. That's expected. But get this, the incorrect label reward still yielded a plus 24.1% gain. And even the completely random reward resulted in an astonishing plus 21.4% gain.
That's incredible. Rewarding incorrect answers or completely random ones still makes the model better at math. It defies logic.
Right.
We have to get to the bottom of how this is possible. But before we solve that puzzle, you mentioned divergence. These surprising gains didn't happen for all models.
You're right to highlight that. And yeah, similar trends were observed on the AMC benchmark for Quinn models too. Spurious rewards actually approached the performance of ground truth labels. The random reward, for instance, gave a 21.4% gain compared to roughly 27-29% for ground truth or majority vote. Even on AME 2024, which is a significantly harder benchmark, the format reward achieved a plus 10.3% gain, nearing the ground truth's plus 15.3%. An incorrect or random reward still delivered impressive 10.2% gains for Quinn.
Okay, so Quinn models seem uniquely receptive to this weirdness.
Exactly. But here's the critical divergence. While Quinn models show these robust and surprising gains, other models like ULMA 2 and Llama 3.1 exhibit minimal improvement. Or, in some cases, their performance even degraded after training on these spurious rewards.
Okay, so it's not a universal thing.
Not at all. And this strongly suggests that differences in their pre-training, the vast knowledge and abilities they acquire before RLVR, are a key factor here. What they knew before this specific training really matters.
That's a huge practical warning then, coming straight from the paper itself. It means the findings from one model family, like Quinn, don't necessarily generalize to others. RLVR research often focuses heavily on Quinn models because they're good at reasoning and their weights are open. But if we only test on them, we're getting a skewed picture. We truly need to test on diverse models to understand the broader landscape.
Absolutely. And this is where the researchers didn't just report these baffling results, they diligently dug into why this divergence occurs. Their core hypothesis was that differences in pre-existing reasoning strategies, basically, ways the models already knew how to think instilled during pre-training, play a huge role. It's not just about what the model learns during RLVR, but what critical capabilities it already knows how to do.
And the standout superpower they found for the Quinn models that seemed to unlock these surprising gains. You mentioned something, code reasoning.
Yes, exactly. The Quinn 2.5 Math 7b model in particular demonstrated this unique pre-existing capability. It frequently generated Python code to solve math problems, even without being explicitly asked or having an external tool, like an interpreter, to run it.
So it's like thinking in code internally.
Sort of. For instance, for a distance formula question, a Quinn 2.5 Math 7b solution wouldn't just give the answer. It would include Python code like import math, define variables, calculate distance, make its math.sqrt, dx2 plus d-die2, and even provide the numerical output on that calculation. And crucially, this code reasoning was highly predictive of correctness for that model. Quinn 2.5 Math 7b had an impressive 60.9% accuracy when using code, compared to only 35.0% using natural language alone.
Wow, big difference. And other models didn't do this.
Right. This contrasts sharply with other models. They categorize them. No-code models like Llama and some ULMA 2 versions simply didn't generate code. And then there were bad code models, such as ULMA 2.7b SFT and a different Quinn 2.5 variant. They attempted to generate code, but their code generation actually correlated with worse performance.
So they tried, but it actually hurt them.
Exactly, which really highlights the distinct pre-existing strength of the Quinn math models in this specific area. They didn't just try code, they were good at it already.
Okay, so Quinn math models come pre-equipped with this code-solving superpower. But how do these weak, even nonsensical rewards manage to activate it? It sounds less like teaching new math and more like nudging the model to use a skill it already possessed, maybe more often.
You've hit on a core insight there. The study indeed found a strong correlation. As training with weak or spurious rewards progressed for Quinn 2.5 Math 7b, both its overall accuracy and its frequency of using code reasoning went up significantly, quickly reaching around 90%.
90%. So it really leaned into the coding.
It did. But interestingly, with ground truth rewards, the good feedback, while accuracy still increased, the frequency of code usage eventually decreased.
Oh, why would that be?
Well, the hypothesis is that with high-quality ground truth rewards, the model might be learning more fundamental, real knowledge about the math itself, or perhaps finding more efficient natural language reasoning paths. It didn't need to rely solely on its pre-existing code-solving trick as much.
So for the weak rewards, it seems like the model wasn't necessarily learning new math concepts, but was instead being pushed or maybe finding it easier to switch to a more effective strategy it already had in its toolkit. That's a subtle but really important distinction.
It is. And the analysis of reasoning strategy switches is key here. For WIST and spurious rewards, Qwen 2.5 Math 7b primarily improved because problems where it initially used natural language reasoning switched to code reasoning. The researchers called these lang code transitions. This switch led to significant performance increases specifically on those problems.
Right, because the code strategy was just better for that model on those problems.
Exactly. And this pattern was much less pronounced or even absent when the model was trained with ground truth rewards. It reinforces the idea that spurious rewards primarily amplify an existing effective strategy rather than teaching a new one from scratch.
Okay, that's starting to make more sense. And to really nail this down, they even tried experiments to, like, force the models to use code or stop them from using it. It sounds like they wanted to isolate the impact of this code reasoning ability.
Precisely, like conducting a controlled experiment. And the results were quite telling. First, to induce code reasoning, they simply added a prompt like, let's solve this using Python.
Yeah.
For Qwen 2.5 math models, this led to significant accuracy boosts. Qwen 2.5 Math 7b, for instance, gained another plus 15.0% accuracy on Math 500 just from that prompt.
Just telling it to use Python made it better.
For the models that were already good at it, yes. But for other models, this prompt actually degraded their performance.
Because they weren't good at code reasoning to begin with.
Exactly. It's entirely consistent with their lack of effective code reasoning. Trying to force them made them worse. Similarly, rewarding the string Python during RLVR also yielded gains specifically for Qwen 2.5 math models, but not for others.
Okay, so that confirms the benefit for Qwen. What about stopping them? Inhibiting code.
Right. Conversely, they experimented with inhibiting code reasoning. They designed compound rewards that specifically punished responses containing Python strings. For Qwen 2.5 Math 7b, this effectively reduced the gains observed from spurious rewards.
Which confirms code reasoning was driving those gains.
Precisely. But intriguingly, for the bad code models, like Ulmo 2.7b SFT.
The ones where coding made them worse.
Yes. For those models, inhibiting code reasoning with these compound rewards actually improved their performance.
Wait, punishing code made them better.
It did, because it steered them away from a suboptimal strategy they were prone to using badly. It's like telling them, look, don't try to code, it's not working for you. And they actually got better overall by not using their weak code skills.
Okay, wow. That paints a really clear picture of how important that pre-existing code skill was for Qwen and how detrimental it could be for others, but I'm still stuck on the random rewards. How can pure noise possibly train an AI model? You'd think if you're rewarding half the correct answers and half the incorrect ones completely at random, it would just average out to nothing. Zero signal. My mind is genuinely blown by this one.
This is where things get really subtle, and the behind-the-scenes hero, or maybe accidental amplifier, comes in.
Right.
The optimization algorithm itself. Specifically, it's a method called GRPO, Generalized Reinforcement Learning with Policy Optimization, and a feature within it called the clipping mechanism.
Okay, GRPO, clipping mechanism. Sounds technical.
It is a bit, but think of GRPO as the coach telling the LLM how to adjust its game based on the rewards. Now, GRPO does something important. It normalizes rewards, essentially trying to balance them around a mean of 0. So it's not simply rewarding correct answers more often in a straightforward way. The core hypothesis here, and this is the crucial part, is that the clipping mechanism within GRPO creates an asymmetric bias.
Asymmetric bias, meaning it doesn't treat all possibilities equally?
Exactly. This bias systematically favors and amplifies patterns or strategies that the model already generates with high probability during its pre-training. It's like the algorithm itself has a built-in preference for reinforcing behaviors the model is already good at, almost like an accidental talent scout for pre-existing skills, even when the feedback signal itself is just noise.
So the algorithm itself isn't neutral. It has a bias that accidentally latches onto whatever the model is already good at, even with completely random feedback. That's quite an aha moment. But wait, if it's random, how does the algorithm even know what to amplify? Isn't it just noise? How does it distinguish the good pre-existing skill?
That's the really clever, or perhaps accidental part. It doesn't know what's good in terms of correctness from the random signal itself. The signal is noise. But it's about how GRPO's clipping mechanism interacts with the probabilities of the model's outputs. When the model already generates a certain pattern, like producing Python code with high internal probability, the algorithm's clipping bias systematically favors and amplifies those high probability patterns. The randomness acts like a general, non-specific nudge in all directions, But the algorithm's internal structure, the clipping, preferentially catches and reinforces things the model was already likely to do.
Ah, okay. So the randomness provides the energy, but the algorithm's bias directs that energy towards reinforcing existing strengths, like shaking a box of mixed nuts. The Brazil nuts, the high probability outputs, might naturally rise to the top because of the physics, the algorithm
What's a
bias.
decent analogy, yeah.
Yeah.
And they validated this empirically. When they turned off this crucial clipping term in GRPO, basically removed that bias.
Let me guess. The gains from random rewards disappeared.
Completely vanished. The model's code reasoning frequency no longer increased with random rewards, and the performance improvements were gone. This strongly implies the reward signal from random rewards isn't really about the randomness providing meaningful direction. It's more like an artifact of the optimization algorithm's inherent bias towards exploiting existing priors. This explains why random rewards work for Qwen 2.5 math models, which have strong useful code reasoning priors for it to latch onto, but fail for other model families that lack these beneficial pre-existing capabilities. The algorithm acts as a filter, reinforcing only what's already strong and useful within that specific model's repertoire.
Wow. Okay. That makes the random reward result make sense, finally. It's not the reward, it's the interaction with the learning process itself.
Exactly. And if we connect this to the bigger picture, this deep dive reveals a pretty profound truth, I think. The effectiveness of reinforcement learning for LLMs seems deeply intertwined with their pre-existing reasoning patterns. RLVR isn't necessarily teaching brand new capabilities from scratch in these cases, but rather amplifying and solidifying behaviors that were already buried within the model from its massive pre-training. It's less about creating superpowers and maybe more about unlocking latent ones.
So what does this all mean for us then? This research feels like a powerful reminder that when we're building and refining AI, the starting point, the pre-training, matters immensely. What the model knows before we try to fine-tune it is critical, and it really highlights the need for careful scrutiny and diverse testing in AI research, pushing beyond just single model families like Qwen to truly understand what's happening under the hood. What works for one model might not work for another, and sometimes the simplest explanation for a surprising gain isn't some magic in the reward signal, but actually a subtle interaction with the training algorithm itself.
Absolutely. And it leaves us with a really important question to ponder, doesn't it? Given that even seemingly nonsensical reward signals can unlock latent abilities in certain models, largely due to these algorithmic biases, what other subtle biases or amplification effects might be at play in current large language models that we haven't yet fully uncovered? Could they be influencing model behavior in ways we don't even realize yet?